fx, fy, fxx, fxy, and fyy are continuous. Okay, so let's assume that f has all these partial derivatives, continuous. Then next define what you call the discriminant of it. Okay, and the discriminant of this f is really evaluated at point AB is a quantity that goes like fxx evaluated at AB times fyy evaluated at AB minus f squared of xy, and that's what makes it different actually from one dimension actually. Okay. So this quantity is, I'm calling it a discriminant. It has a relationship with what you call the Fresher derivative. So the Fresher derivative has a matrix actually, and this is really the determinant of matrix. That's really the determinant. So what we are actually saying is, look at the Jacobian. Okay? Look at the Jacobian of, what do you call, what do you say? It's a bit different from Jacobian. Okay? So it's a special kind of a matrix. We'll talk about it in the next class. Okay? We have a little time, so let me just.
सर अगर इस टाइप का कोई फंक्शन है तो उसकी क्रिटिकल पॉइंट नहीं होगी ना?
क्या मतलब?
मतलब सर अगर से सपोज ये
we'll have a set of the points which are the critical points.
और वो मतलब बहुत ज़्यादा हो सकती है.
There are infinite number of.
Infinite of
You can have the infinite number of critical points. That's what makes it different.
partial derivative.
ठीक है? So this is really what you call the discriminant of it. Okay. So we'll talk about it now. That's this discrimination. And another is that if you want to know about that what kind of point AB is a point, just really look at it. You look at this guy out. Look for this discriminant. Okay? Number one. If for a point AB, this quantity D is positive. Okay? D is positive. In other words, D of AB is positive. Then what? This AB is relative what? Minimum. Okay? Why? We'll see in a minute. At least, looking at the definition of the discriminant. And if D of AB is positive, so if AB is positive, okay, I should write one thing actually there. D is positive and fx of AB is also positive. Okay? Fx of AB is also positive. Then AB is relative minimum. And second is, if this discriminant is positive and the derivative with respect to AB is negative, okay, then AB is a relative maximum. ठीक है? तीसरी condition. If D simply turns out to be negative, okay? Simply turns out to be negative, then AB is a saddle point. Is a saddle point. Okay? So which is really analog of point of inflection here.
Yes.
Okay? And this is the fourth situation. You can say that if D is 0, okay, if d is 0, then the situation is, inconclusive, that this AB can be a minimum, can be a maximum, and can be a saddle point actually. So it could be all three, one of all three. So if discriminant is 0, then AB can be minimum, maximum, or saddle
Sir,
point actually. ठीक है?
sir, so is there any other necessary condition for with this condition d is equal to 0 for that we have particularly minimum, maximum or saddle point?
Just if d equal to 0. D equal to 0.
So precisely we cannot judge that.
We can't just sell this. Then you have to use some other sources to find, and there are other sources to find the maximum. ठीक है? And I guess this quantity is determinant of something what you call the Hessian matrix actually. Okay? Which is closely related with the Fresher derivative. It has to something to do with the Fresher derivatives. Second order derivative. Okay. But keeping in view this description, you can still make sense of some of things. Now, imagine d is positive. So this means that this difference is positive actually. Okay? This difference is positive. In the difference, this second quantity is non-negative. So imagine a situation, I have alpha and a beta, and I have a difference, and this difference is positive. And now I know about the beta that it can't be negative actually. So this is greater than or equal to 0. So what conclusion you can have about alpha?
Alpha greater than beta.
Alpha greater than beta.
वो तो वैसे भी पता चल रहा है इसमें कौन से सांस मारते हैं अल्फा is greater than beta are sure alpha is greater than beta but can alpha be negative? Alpha can't be negative ठीक है अगर alpha negative नहीं है so then alpha is really the product of what do you call these two quantities and you know about this quantity that this is positive. Now the product is positive and fxx is positive. So tell me what could be the fyy?
It must be positive, sir.
It must be positive. It can't have other sign actually.
Great.
Okay? So he's clever. He's not writing fyy must be positive. Because that would be a violation of what you call the Occam-Razor principle that don't multiply your assumptions. So why should I write something in assumption that I can deduce actually. Okay? So when fx is, so what does this mean? So if the discriminant this is positive, the conclusion that we reach is that fxx is also positive and fyy is also positive. And what is the meaning of fxx and xy is positive? So fx is telling you the slope of the tangent line, and fxx is telling you, what? How the slope is changing, its behavior actually, and it is positive. In other words, that you are gaining more and more and more and more slope actually along x-axis when you are moving along x-axis, and fyy is also positive. So what does this mean? So this means that if you move along what you call y-axis, the curve is gaining other, what you call, the surface is gaining, or the tangent line is gaining what? More and more slope actually. And if it is gaining the slope, that point, in these two principal directions, so it's like you are, okay, so here you have a less negative and you become, you have a negative slope and less negative, 0 and then positive. So you are gaining the slope along x-axis and along y-axis. So you are talking about a valley. Okay? So what does this analysis is revealing that without even looking at the function, you are saying that how does it look like around the point AB? So it looks like a blob actually. Okay? So it's, what do you call, if you say in in your previous language is really the concave up, but the concavity is about curves actually. Okay, but you can have something similar notion actually. Okay? Is it making sense? So this makes sense. So if the D is positive, then it makes sense that this AB must be relative minimum. Okay? So it's not just got to give in fact, but you can really make sense of it. So if the D is positive, but F is negative. So you have this difference positive, and this guy is positive, so alpha must be positive, and F is negative.
So why be negative?
Why would be negative?
This will be greater than this.
Because if the product is negative, and I know the one of the factor is negative, the other would be negative as well actually. Product positive, one factor is negative, the another must be negative as well. So in other words, in both cases, what is happening actually? So your tangent line, okay? So if you are moving along the tangential direction, you are doing what? You are losing the slope actually. Okay? In both directions, we are talking about that. Something concave down actually. Is it making sense? And if D is negative, so when D is negative, what happens now? Now that would be an interesting situation now. I have alpha minus beta, where the beta is positive. Okay? Beta is positive, in other words, non-negative. So what you can say about negative beta? So it's non-negative actually. As I
Beta must be.
So you greater over alpha.
and I have an alpha, and I know about minus beta. If I look at this minus beta, this entire quantity is a negative quantity, and this whole quantity is a negative quantity. So what you can say about alpha? It must be a negative quantity. Now if D is a negative quantity, in other words this alpha is a negative quantity, in other words this product is a negative quantity, what you can say about this product? They have the opposite signs actually. Okay, so if in one direction you are going, you are losing the slope, from the other direction you are gaining the slope actually. So it must be like a valley actually. Okay, is it making sense? It all makes sense. While D equal to 0 is crazy. So you can't conclude anything. Is it making sense? Okay. You have it. That's your second derivative test. And it makes sense. Now this test makes sense because you understood the second derivative test.
In one dimension.
I hope in one dimension actually. Okay. Anyway. Shall we do an example? Self-explanatory. वैसे है तो नहीं कुछ करने वाला है. Let's do one. Let's do one example. Okay? And I'm leaving these notes for you to work out all other examples and then we'll go more for it. Okay. So imagine I have been given a mysterious surface which I have no idea how does it look like unless I ask for the help from what do you call GeoGebra, mathematical or something like that. And I want to know the critical points and I want to classify them. So what should be the first one? Find the critical points, compute the partial derivatives. Okay. This guy is clever. He's, because he's taking the cubic equations, because then you're going to remain with the quadratic equation.
Yes,
You can solve it. Okay, so what you're going to get? So 0 and
3x square
3x square
minus 3y.
minus 3y equal to 0. Okay. And Fy is what? 3y square minus 3x. You equate it to 0. And you're going to equate it, what you're going to get? You're going to get 1 as y equal to x square, another x as y square, and solve these two curves actually. Okay. So in other words, So you just need to find the intersection. So how are you going to find the intersection? So the y is going to be x power 4. Huh? So if you have x power 4,
y power 4
x square is going to be y power 4, and then you know one value of the y is going to be 1. Okay? And for other value you need to solve this cube root. Okay? And what would be the other real value, for example? Real value. You forget about the complex value because that doesn't make sense, because you're going to have 3 roots and you're going to have 3 cube roots of the unity, but other 2 are going to be complex. One is going to be real.
एक जीरो होगा ना सर? एक जीरो होगा ना सर? अगर y4 को
हाँ ठीक है, एक y equal to 0 होगा,
एक 1 होगा,
and y equal to 1, and other 2 are going to be complex. ठीक है? Good. And if you know the y equal to 0 and 1, then you know the x will become 0
and 1 sir respectively.
and x will become 1 as well. So the 0, 0 and 1, 1 are really the critical points. Okay? So I have to classify that. So I need to do just run the algorithm actually. Okay? If you are lazy enough, you can write a code and that can calculate all these things for you. लिख लेंगे कोड टेस्ट के लिए?
दोदा
जी सर,
आप भी लिखे ना, दोदे ने करना है काम आपके साथ।
तो साथ मिलके करेंगे।
साथ मिलके करना।
इंशाल्लाह।
ठीक है? Anyway, खुद कब सीखेंगे? This is important. Computing is a must actually. हमारे तरह थ्योरी करते रहो। ठीक है जी, so what should I calculate next? So let's calculate fxx, which is going to be 6x, fyy, which is going to be 6y, and let's calculate fxy, or fyx doesn't matter, okay, which is going to be what? So, minus -3, okay. And then the d is going to be what? D at, so the d of xy is going to be fxx and fxy, so we're going to have 36xy and -9. Okay? And then we need to do what? Just look at the value of the d and value of the, say, one of the double derivative actually. So we're going to get d of 0, 0 is really -9. So there's nothing more to do. So if you get a negative, fine. Okay? So that's a saddle actually. The origin is a saddle. Okay? So that's 0, 0 is a saddle. So in other words, at least around the 0 I can make a picture in my head actually that okay, this could look like anything, but at least you know around the 0 it should be, one way it should be like that, another way it should be like that. Okay? How about 1, 1? So the d evaluated at 1, 1 gives you
27
25. So 25.
20
This may be long.
27.
27, but I have this one. अहमद खान की बातों पे यकीन नहीं करना चाहिए।
मैं 27 करके फिर 25 कर दिया उसने।
चलो ठीक है। So what is the next thing? So you need to compute fxx, for example, at 1, 1.
ये 6 होगा।
This is positive, so what are you going to say? And this 1, 1 is a minimum. Okay. At point 1, 1, it's a minimum. In your calculus course, have you done what you call the curve sketching actually?
Yes sir.
Okay, the curve.
One dimension.
Okay, so what for curve sketching, what you need to do? You need to know the critical points, and you need to know the maximum, minimums, and you need to know the asymptotes actually.
Yes.
And if you think carefully about it, you can also do something similar actually. Even in other words, without really even looking at the surface,
We can draw something.
you can draw really a rough approximation of the surface actually. At least I know at 2 points how does it look like.
Yes.
Okay. Okay. Is it making sense? Good.
सर सरफेस को तो ये फर्स्ट डेरिवेटिव टेस्ट और सेकंड डेरिवेटिव टेस्ट के बाद हम ये विजुलाइज तो कर सकते हैं कि ये होगा, लेकिन ड्रा करने में तो फिर मसला होगा ना। उसका मॉडल बना सकते हैं अगर हमारे पास कुछ चीज़ें हों, तो एक 2 डायमेंशन पेज के ऊपर इसको ड्रा करना, ये जो हमारा, तो ये तो बड़ा मुश्किल होगा क्योंकि बाकी अगर हमें मॉडल बनाना हो तो फिर हम उसका फिर कुछ ना कुछ कर सकते हैं, क्योंकि हम 3 डायमेंशन के अंदर वो चीज़ें, वो सरफेस को उस तरह से
even there is what do you call, you can do what do you call surface sketching. If you want to do surface sketching, then level curves play an important role actually. I mean, if you want to study, for example, how does this guy looks like, so you need to look at the different kind of a level curves of it actually. So we don't have time for it, but I'll send you and upload a lecture actually, so you can watch it at how to do the surface sketching actually. You can look at the level curves there. So this guy looks like this actually. So let me try to draw it. It's a difficult thing, but okay. So it goes like this. Okay. Okay. You have so you have a blob here. So you're going to get a copy sheet from here. Let's not try to draw it. Very bad at drawing pictures. And, some people are very good at drawing pictures actually. They can draw very technically. Is it making sense? So roughly you have the way you have, for example, and I'm finishing, just finishing, not writing anything, just telling you, so you need to read it for yourself actually from here. That if you have, so in one dimension, I mean if you're talking about the global maximum or minimum or absolute maximum or minimum, then you do what? You say that if your function is defined on a closed interval, then there must be some, what is called, maximum and minimum in that actually. So you also have an analog extreme value theorem in 2 dimensions. So what you're going to say? You're going to say, if you have a function that is defined on a closed surface actually. So in other words, you have a kind of a really a surface, okay, that is really the outputs of, for example, this, okay, are going to look like this. It's going to look like something like this with shadow of this actually. And if this domain is closed, then this guy must have a maximum and minimum actually. If the maximum and minimum occur within what do you call surface, fine, otherwise they will occur on the boundary.
Yes.
So like in the one dimension.
Yes.
So either it's going to exist on the interval A to B, within the interval A to B. If not, then A and B are really, one of the A and B is the maximum and the minimum.
सर उधर इस तरह का एक थ्योरम था 1 डायमेंशन में, यहाँ भी वो थ्योरम है हाई डायमेंशन में। ये जो थ्योरम
मोस्टली थ्योरम्स हैं 1 डायमेंशन
नहीं, वो जो इंश्योर करता था कि एटलीस्ट उसमें ग्लोबल मैक्सिमम होगा, ग्लोबल या पता नहीं रिलेटिव।
That's what I'm talking about. So this is what you call the EVT, extreme value theorem.
Extreme value.
So you have a 2-dimensional extreme value theorem and hence in 3 dimensions as well.
Extreme value.
It's called extreme value. You can generalize it to that dimension. So you have this extreme
सर
value.
इसके इसमें मतलब ये सैडल भी है और इसकी मिनिमम पॉइंट ये वाली, मतलब सर ये जो ग्राफ
हाँ, यानी at zero it goes like a circle. Okay, and at 1 उसी के करीब you have a blob actually. I mean if you, I don't know whether you can see this or not. If you want to have a look, you can have a look at it. And it makes sense actually. It really makes sense. If you look at it. look at the origin, it looks like a saddle. Okay? Around the one, it has a minimum. Sensible shape. As per our expectation.
सर इसको मतलब हर पॉइंट्स पे चेक करना पड़ेगा कि क्या पता सर कहाँ पे मिनिमम हो कहाँ पे
हर पॉइंट नहीं, क्रिटिकल पॉइंट्स ढूंढने पड़ेंगे, लाइक यू डू इन वन डिमेंशन.
सर उसके लिए ये भी ढूंढना पड़ेगा ना.
Yes, that's what the mistake. So you need to find where the gradient of the function is there. So just figure out those points and then just check these conditions at those points you're going to have to equal.
सही है.
ठीक है. And we haven't proved it. I mean, if you wish, you can see the proof of it. This factor is really a determinant of a special kind of a matrix. Okay. And this statement makes sense. I mean, if you we discussed it. Okay. See you next week.